Okay, net change theorem is the second part of 5.4, and it's really the meat of 5.4. The net change theorem, and I'm going to try to explain it to you in two ways. The first way I'm going to try to explain it to you is with reference to a physics problem, okay? A very, very easy physics problem. We're talking, middle school kind of physics problem. But I'm actually going to show it to you in terms of a graph, okay? Let's say that I have a graph where I'm going to actually graph my velocity function, okay? And let's say that I am in my car and I'm driving and I have the cruise control on, okay? And my v of t is equal to 50. I'm going down the road, I've got my cruise control set at 50, and that's just fine with me, and I'm just going to go ahead and keep on trucking that way. And you're thinking to yourself, well, I checked the clock at 2 o'clock, and then I checked the clock at 5 o'clock, and I've been driving that whole time for 3 hours. I wish that there was a way for me to figure out how far I had traveled in that interval, right? Well, you got to remember that velocity is just another name for rate, okay? And down here is time. Well, here's the thing. Distance equals rate times time. So the area of this rectangle right here should be the distance, okay? Well, here's the thing. If I take the integral from 2 to 5 of 50, which is my velocity function, dt, isn't that 50t from 2 to 5? And isn't that 50 times 5 minus 50 times 2? Or, if I want to factor out the 50, 50 times 5 minus 2. What I'm trying to underscore here is this. When you integrate a rate function, you're going to wind up getting the net change of the original function. So let me put it this way. You know that if I go from a to b of f of x dx, that actually winds up being big F of b minus big F of a. Remember that all definite integrals imply a difference. Okay, well, let's make this a little more specific. Let's go from a to b of v of t dt, and we usually use s of t for position, right? So it's s of b minus s of a. So what does this difference mean? It means that if I integrate the velocity function from a to b, I get the difference in the position at b and the position at a. Well, if I take one position and subtract another position, don't I get the net change in position? I get the displacement, okay? If I basically figure out a way to calculate where the particle or whatever it is that I'm talking about is at B and where it is at A, the difference is the distance between them. Well, this doesn't just work for physics problems. It actually works for any rate function that you want to employ. Anytime I'm going to integrate some rate function, okay, rate function, and we'll call it dx, what I'm going to get is I'm going to get position at b minus position at a. And I use position, but it could be like the rate function could be r of x is equal to, some expression in terms of x in gallons per minute. Okay, let's say that r of x, or r of t, or whatever you want to call it, is a rate function which tells you how fast a swimming pool is being filled up. You know, you basically threw the hose into the swimming pool and you're filling up the swimming pool, and you have a rate function which tells you how fast in gallons per minute that it's filling up. Well, if you go ahead and integrate that rate function, you're going to get the net change in gallons from A to B. And if it weren't gallons per minute, let's say it was, you have a function which tells you how many people go through the gates at a baseball stadium to get into the game at any time t, and it's people per minute. Okay? Well, if you then integrate from A to B the rate function in people per minute, you're going to get the amount of people that entered the stadium, the net change in people from A to B. Okay? So anytime you integrate a rate function, you're going to wind up getting the net change in the original function, of which this is a rate. Okay? So basically you're going to get the net change in the units in the numerator of that rate function. Okay? Well, let's go ahead and let's do an example that is very much in terms of physics and velocity in a particle. Let's say that we have a particle traveling along, let's say it's along the x-axis, okay? And my velocity function is t squared minus 3t plus 8, okay? That describes the velocity of the particle at any time t. Now, let's say that I want to find, let's find the displacement between t is equal to 2 and t is equal to 4. Now, displacement, that's a very key word, and I'm going to talk about that in just a minute. Notice that it didn't say total distance. It simply said displacement, okay? Notice that this is a net change theorem, not a gross change theorem. So what I need to do is, if I want to find how far away the particle is at t is equal to 2 from when it is at t is equal to 4, I simply have to integrate from 2 to 4 the position function, the velocity function, and this has to give me the position at 4 minus the position at 2, not taking into account any constants, right? Because remember, when you're doing a definite integral, you don't use the plus c because the plus c's fall out, okay? So this is going to give me 1/3 t cubed minus 3/2 t squared plus 8t, and I'm evaluating it from 2 to 4. Now, I'm going to go ahead and cheat and actually use my calculator in order to get me this this value, because I just don't want to burn too much time in this video. And it's going to be 16 2/3. Okay, 16 2/3. So you don't know necessarily the position at s of 4. You don't know the position at s of 2. But you know that the difference between them is 16 2/3. Okay? You know s of 4 minus s of 2 is 16 2/3. Now, this was actually a strategically chosen problem because there are going to be some particle motion problems where displacement is not the same thing as total distance. Okay, and let me go ahead. Let's say that this is s of 2. This is s of 4. This right here is displacement. how far they are apart at those two moments. Now, in order to go from here to here, did it necessarily travel in that straight line? And the answer is no. I mean, there's a infinite number of possibilities. It could, have done that, right? And if it did do that, then I have a problem, okay? Because the integral that I set up will give me this. This is s of 4 minus s of 2. That's not really showing up all that well. Okay, whatever. Okay, this right here is s of 4 minus s of 2. That is the displacement. This whole thing, however, is the total distance. Now, for the particular problem that we just did, they're one and the same. And I happen to know that because the velocity function right here does not change direction. I know that the velocity doesn't, the position doesn't, like the direction doesn't change because this velocity function will always be positive. And I know that because of what we've talked about in terms of perfect square trinomials and the relationship of any quadratic to sort of the related perfect square trinomial, right? The perfect square trinomial with those first two terms would be plus 9/4, right? This would be the perfect square trinomial. And of course, any perfect square trinomial has its vertex on the x-axis. This represents a vertical phase shift up from this perfect square trinomial, okay? And therefore I know that this quadratic is always positive. If velocity is always positive and never negative, or just always the same sign and never changes sign, then displacement and total distance are the same, right? Because from here to here, this represents v of t is positive. Right here, this is v of t is negative, right? It's moving in the opposite direction. So there will be some where you have to differentiate between displacement and total distance. But you have to determine before you do that whether the quadratic or whether the model which represents the velocity actually changes sign, and if so, where, okay? We'll get to an example like that, just not right now, okay? Let's go ahead and move on to another problem. How about we do, sorry this is just a little bit grainy. Actually, it shows up better on the camera than it does in real life. All right, water flows into an empty reservoir at a rate of 3,000 plus 20t liters per hour. What is the quantity of water in the reservoir after 5 hours? Okay. Well, I happen to know that it starts as an empty reservoir. Okay. So, if you want volume at 0, it's 0. Okay. So the rate function, and we'll call it r of t, is equal to 3,000 plus 20t. Now here's the thing. This is linear. So you could actually do this geometrically, right? It's going to wind up being a trapezoid. And you can find the area of a trapezoid because, it's going to do something like this, right? It's going to start at 3,000. It's going to go up from 20. It's going to go from 0 to 5. And it's easy enough to find the volume of a trapezoid. And so, you could actually start with something like this and do it by integration, do it by calculus, and then check your answer geometrically. That would be very, very easy, and that's probably why the person who wrote this problem wrote it the way that they did. But let's go ahead and just do it by means of calculus. We know that the integral from 0 to 5 of r of t dt is going to be v of 5 minus v of 0. Okay. Well, we already know that 0 is 0. So let's go ahead and actually do it and we have 20t plus 3000 dt, and I know that that winds up being 10t squared plus 3000t, and that just confirms that, it doesn't confirm that v of 0 is actually 0, because remember, you're disregarding any constants associated with the volume function. It just so happens that you were given the information that it's an empty reservoir at time 0. So from here, what we get is 10 times 25 plus 3,000 times 5, and so that's 250 plus 15,000, or 15,250. Okay, and in terms of units, since the rate function was in liters per hour, and you actually integrated from 0 to 5 hours, you are left with the units of liters. 15,250 liters have been dumped into that reservoir over those 5 hours. And it was basically, you arrived at the net change, right? Net change based upon the integral of the rate function on the interval that was actually designated. Okay, that brings us to a nice stopping place for this particular lecture or video, or whatever you want to call this. I'll do one or two more on this. I mean, it really isn't all that difficult. The only time it gets tedious is something that I've already foreshadowed, when you actually have a rate function that changes sign, and we'll do at least one of those in the next video, or perhaps a third video if that's necessary for time reasons. Okay.